Thanks, Yizhi, for the introduction, and I would like to thank all of the organizers for bringing about this fruitful program and conference. Today, I will talk about simple strong symmetry breaking and the long-range order that occur in an open system. So, before I proceed, let me acknowledge my collaborator. This was based on a recent work that was on the archive last week, and it's driven by Pablo Sala, who is from Caltech, Masaki Oshikawa from UTokyo in the audience, who is here to take hardcore questions, and also Sarang from Princeton University. And in the meantime, there's also a concurrent work on strong to weak symmetry breaking open quantum systems by the audience from the Perimeter Company. Okay. So the theme of this conference is about exotic gapless state. And from all of the talk we encountered during the conference and program, it turns out that symmetry plays an important role to engender exotic gapless state. Like last week, they gave a talk about spontaneous symmetry breaking one spatial dimension, 1+1 dimension, where the gapless degree of freedom can be driven by Goldstone bosons. And this week and throughout the program, we have a zoology of nice talks on deconfined quantum criticalities and Dirac spin liquids, where for deconfined quantum criticality, sometimes we have some emergent symmetry that is essential for the emergent anomaly, and hence modified some of the critical behaviors. And in the Dirac spin liquid, the low energy effective theory is driven by the emergent U1 gauge field. So there we have emergent gauge symmetries. And from Hama's talk yesterday about CFT, about critical theories, conformal symmetry sometimes play an important role, and there can even be some emergent symmetries that was not present in UV Hamiltonians. And from Potter's talk last week, and also part of Xiaogan Wen's talk, it turns out that at the boundary of some symmetry-protected topological phase, the gapless degree of freedom, the symmetry plays an important role because the symmetry act on the gapless degree of freedom in an anomalous way and hence protect the gapless node. And also for some of the intriguing talk this morning about Fermi surface, it turns out that on the Fermi surface, the gapless degree of freedom has an emergent LU1 symmetry. Okay, so let's proceed. Today I will talk about symmetry and especially some type of symmetry breaking in open quantum system. So let me talk a little bit about a setup. Suppose I prepare a pure wave function, which can be locally entangled or highly entangled. And then I let it interact with the environment and entangle with the environment degree of freedom. During this process, the system is being constantly measured by the environment degree of freedom. So our initial pure wave function eventually becomes a general mixed state that can be represented by a density matrix. And this process is known as decoherence. And for the exploration of decoherence in the open system, it has been diverted into several trends. And one trend is, suppose we begin with a long-range entangled wave function, say a CFT wave function or the ground state wave function of the toric code that is long-range entangled, and let it decoherent for a finite amount of time. What is the fate of the quantum ordering in such kind of mixed state? And this direction has been explored by a large number of pioneers, some of which are already in the audience. Another question is actually trying to pursue from the opposite trend. So suppose I begin with a totally trivial wave function, pure wave function, say a spin polarized state. Can decoherence engender or trigger something interesting? Like, can decoherence trigger some type of long-range order in a mixed state? And today I will provide a simple example that manifests decoherence can trigger some type of long-range order. And I will talk about how decoherence can trigger a strong symmetry breaking induced by local quantum channels. Okay, so let me first review what is the concept or definition of symmetries for quantum phases. So for a pure state, a pure wave function, the definition of symmetry was pretty simple. When I say a wave function is invariant under symmetry G, that means apply the symmetry transformation, the wave function is invariant up to some global phase vector. For mixed state, all of the information is encoded in a density matrix. And hence, for the same symmetry, we can have two notions. The first notion is called strong symmetry, and in some literature, it is called exact symmetry, such that the symmetry operator, UG, only act on the left part of the density matrix or only act on the right part of the density matrix and make it invariant up to some global phase factor. If a mixed state has a strong symmetry, that means all of the eigenvectors are eigenfunctions of the symmetry operation, and they carry exactly the same quantum number. And another notion is called weak symmetries, and sometimes we call it average symmetry, such that the symmetry operation should act on the left and the right part of the density matrix simultaneously, and this leaves the density matrix invariant. And hence, if a density matrix only have weak symmetries, in principle, we can have an incoherent sum of different symmetry breaking patterns with the same probability. And for pure state, we know two different pure states defined in the same Hilbert space can be connected by unitary gate. It doesn't necessarily need to be local. And for density matrix defined on the same Hilbert space, they can be connected by quantum channels. So some fun facts about finite depth quantum channels. We know that for finite depth quantum channel, in principle, they have to obey the Lieb-Robinson bound because a finite depth quantum channel acting on a density matrix is equivalent to finite depth local unitary acting on the wave function. But in the meantime, there are a few examples that was already explored telling us that finite depth quantum channel can kill or generate some type of long-range order. And here, some type of long-range order, I have a quote mark here. And what does it exactly mean? This is something I will explain in the next slide. And one typical example was explored by Xu and Wang, so that they figure out there is a one-depth quantum channel that can trigger a spontaneous strong to weak symmetry breaking in a 1D quantum spin chain.
Finite depth quantum channel. What is the definition of finite depth?
Yeah, so let me give you an example.
Yeah. I thought it can only generate long-range order, but not kill long-range order?
Correct. It can generate, but not kill, because it's not the other side. I see. So let's have a warm-up example proposed by Xu and Wang last year. Suppose I have a 1D quantum spin chain, and initially all of the spins are just a tensor product state polarized in the SX direction. And then I make a measurement quantum channel such that I only measure the spin bilinears on nearby site and average over all possible result. And after this process, our initial spin polarized pure state becomes a mixed state density matrix, which can be calculated explicitly. It can be represented by such kind of 1 plus capital X density matrix. And during this process, our initial state is polarized in the SX direction, so we have a symmetry which is generated by an X string on the 1D chain. In the meantime, because I only measure spin bilinears, so this quantum channel also respects the strong Z2 symmetry. And hence, a naive expectation is that my final mixed state density matrix should have a strong Z2 symmetry generated by this X string. Okay, but if we just measure some of the physical observable on this mixed state density matrix, if I measure the two-point correlation function, ZZ correlation function, or any type of correlation function, it turns out to be 0 in the thermodynamic limit. But if I measure some type of Renyi-2 version of the correlation function, where the operator acting on the cat space and the bra space simultaneously, it is non-vanishing and of the order 1. And this is what I mean by some type of long-range order that can only be manifest by a Renyi-2 correlator or any type of correlator that is not linear in the density matrix. Okay. So this is a simple example they demonstrate. But what does it mean by having a non-vanishing correlation function in the Renyi-2 correlator? So let's see. Throughout this process, we have a strong Z2 symmetries generated by the X operators. And if I have a Z operator which only acts on the left part or only acts on the right part of the density matrix, I will say this operator is charged under weak symmetry. And if there's no long-range order for this correlation function, that means the weak symmetry is not broken spontaneously. In the meantime, if I have a Z operators that act on the cat space and the bra space simultaneously, I will say this operator is charged under the strong Z2 symmetry, but neutral under the weak Z2 symmetry. And if such type of operator develop a non-vanishing value of the order 1, this indicates we have break the strong symmetry spontaneously, that is manifest by this correlation function, but weak symmetry is still not broken. So this is an explicit example where strong Z2 symmetry is broken by weak Z2 symmetry. And here we only apply one depth quantum channel where we just measure some local observables and average over all of the outcome. And in quantum information, the finite depth quantum channel is equivalent to finite depth unitary acting on the purified state defined on the enlarged Hilbert space. So the Lieb-Robinson bond still applies. And that is why no matter what type of observable we measure that is linear in the density matrix, it should be short-ranged correlated. And only thing you can probe is something that is nonlinear in the density matrix, like the Renyi 2. So at this stage, an ensuing question one might ask is, first, why such kind of strong two-symmetry breaking can be generated by one depth local quantum channel, and what is indeed the physical interpretation of this Renyi 2 correlation function, other than the fact that whenever I have a mixed state density matrix, mathematically I can always calculate it explicitly.
I missed the part where, is this the definition of weak symmetry broken state, this correlator?
Okay.
Before you defined it as something that's in density matrix invariant under the dagger conjugation, that's the weak symmetry. Mm-hmm. You're breaking that. So why is this correlator the simplest correlator process?
Okay, so first, why does this correlator probes that you have symmetry breaking? Second, is this the real probe of the phase transition? So why this probe? If I say there's a spontaneous symmetry breaking, that means I have to identify an operator that is charged, and such kind of charged operator should have long-range order. And here, I only want to demonstrate that strong symmetry is broken, but weak symmetry is not broken. And hence, I have to identify an operator that is charged under the strong symmetry, but neutral under the weak symmetries. And hence, I have to have a Z operator, charged operator, acting on the cat and the bra space simultaneously. This operator is only charged under the strong Z2 symmetry, but neutral under the. And if this operator develops a long-range correlation, I can say that there is some type of symmetry breaking.
So the operator is CIZJ? What's the operator that's charged on this function?
Yes, so the operator that is charged is the ZI acting on the cat space and also ZI acting on the bra space simultaneously. And here I'm measuring such kind of operator's correlation function where I and J are spatially separated. Yeah, the other question is this really the operator that probe the phase transition? And that depends on how you define phase transition. According to one company's definition about non-invertibility, actually, this operator is not enough, and we need to look into something like the fidelity operator, and probably let me talk about it in the last few slides. Okay, so the question is, what does Renyi 2 correlator really mean here, other than the fact that we can define it mathematically? So because organizer Chen Ke-Xu proposed that this is indeed a condensed matter conference, so we have to visualize everything in a more condensed matter view. So let's forget about quantum channels and try to visualize this process in terms of a purification view. So whenever I have a mixed state density matrix, I can always treat it as a reduced density matrix of a subsystem defined in a purified state in an enlarged Hilbert space. So whenever I have mixed state density matrix, I can imagine I have an enlarged Hilbert space and I have a pure wave function. If I trace out the rest degree of freedom, I get a reduced density matrix, and that reduced density matrix is indeed the mixed state density matrix. So I can always treat it as a partial degree of freedom of a pure state. And based on this approach, whenever I have a quantum channel acting on a density matrix, this is equivalent from the purification view. I add a unitary operator that act on the purified state, where the purified state contains the system qubits of interest and some ancillary qubits coming from the environment degree of freedom. I'm trying to add a unitary operator to entangle them. So these two as a whole is a purified state, is still a pure wave function. But if I trace out the ancillary degree of freedom, the reduced density matrix of the system, the reduced density matrix of a pure wave function is usually a mixed state. So let's try to visualize the quantum channel we introduced a moment ago in terms of a local unitary gate. So now my setup is I have a 1D quantum spin chain that belongs to the system, which is this blue spin chain. And I also have an ancillary degree of freedom, which is another spin chain represented by the red spin chain on the top of that. And my initial state is they are not entangled at all. System spin are all polarized in the x direction. Ancillary spin, the red, are all polarized in the z directions. Now I add a three-body gate to entangle them. And what I will demonstrate is this three-body gate does the same job as the quantum channel. So the three-body gate is something like a control gate. Something like I measure these two blue spins from the system. If they are parallel to each other, then the red spin coming from the ancillary in between remain to be up. If they're anti-parallel to each other, then I flip it to the down direction. So this is one-step unitary gate acting on every three clusters. And after I apply such kind of...
Using IY or using X are the same? Using IY to flip?
Yes.
Can use X to flip?
Yes, it's just that I choose a specific basis. And after I apply this unitary, I get a short-range entangled wave functions. And this wave function has a decorated domain wall structures. So if I have two up spins from the system in between, the ancillary spin also have to be up. If I have up and down, then I have to decorate a spin down from the ancillary. And this decorated domain wall wave function is pretty well studied, and it is known as the ground state wave function of a cluster Hamiltonian, which I will not dig into details. And a few facts of this cluster Hamiltonian is this is a local Hamiltonian, so the wave function is just a ground state of a local Hamiltonian that can be manifest on a lattice model. And this Hamiltonian together with the ground state wave function have two symmetries. One is the Z2 symmetry, all of the Z operator acting only on the ancillary. The other is the other Z2 symmetry, which only act on the system qubits, on the blue qubits. And because this is a short-range entangled wave function, there's no long-range order, but there is a non-vanishing string order. If I measure the ZZ correlation functions of the system, you will see that it is modified by the charge string carried by the ancillary in between. It has a non-vanishing string order. And if I trace out all of the red spins from the ancillary, then I get a reduced density matrix of this wave function. And that reduced density matrix is exactly the density matrix after we apply a pure measurement quantum channel. Okay, so in summary, here I do a simple thought experiment. If I want to get a mixed state, I can begin with a spin polarized wave function at a pure measurement channels and get a mixed state. And this process is equivalent as I first enlarge my Hilbert space by introduce a spin of a chain of ancillary that was not entangled, and then I entangle them into an SPT wave function such that trace out the ancillary red spins. The reduced density matrix of the blue spin exactly reproduce this mixed state density matrix. And on one side, this mixed state density matrix, we know they have spontaneous strong to weak symmetry breaking that is characterized by the Renyi-2 correlation function. And on the SPT wave function, we know that they have some type of non-local string order parameter. So at this stage, an ensuing question one might ask is naively, are they somehow related? Okay, so now let's have a thought experiment. Let me represent the wave function in a tensor representation. So this is the SPT wave function of the purified state. The blue block is the system spins, and the red blocks are the ancillary spins. Now I duplicate another copy, exactly the same copy. And what I will do is I just make an EPR projection such that I project all of the ancillary from the first and second copy into a symmetric EPR pair. After I do the projection, all of the Z charge of the ancillary are somewhat fixed. And after you do the projection, it's not hard to find that the post-projected wave function, after you project all of them to the EPR pair, has a long-range 4-point correlation function with two of which acting on the first copy and two of which acting on the second copy. This is pretty straightforward because previously we have a string order, and if I do the projection, I'm somewhat fixed all of the charge string in between to be even, and hence the string order just becomes this 4-point correlation function. Okay, now I just play a simple trick. For the second copy, I reverted from the cat space to the bra space. And previously, I'm doing some type of EPR projections to enforce them to be the same. Once I revert second copy to the bra space, such kind of EPR projection is exactly the same as inner product the ancillary from the bra copy to the cap copy, which is nothing but trace out all of the ancillary degree of freedom and hence get the reduced density matrix of the systems. So here I doing an inner product which is equivalent to project ancillary pair to EPR, and then previously I measured 4-point correlation function, 2 of which on the first and 2 of which on the second copy. Now I measure this 2-point correlation function, 2 of which act on the cat space and 2 of which only on the bra space, and inner product with the density matrix itself. And this is exactly what we define as the Renyi-2 version of the correlators. And from this simple trick, it turns out that the Renyi-2 correlator has a pretty simple and straightforward meaning in terms of the purification. If we have a purification wave function, it can be any arbitrary purification wave function. Take 2 copies. For the first and second copy, for the ancillary, we just project them to an EPR pair. And then, after the projection, we measure the 4-point correlation function post-projection. This is mathematically equivalent to this Renyi-2 correlators. So what does this tell us? If we have a non-vanishing Renyi-2 correlation function, that means your purified state must have some type of measurement-induced long-range order. Itself is short-range entangled, but if you project the ancillary to some type of specific sectors, the post-projected wave function would have long-range order. Okay, so from this simple game, it turns out that when we deal with a mixed state, the system qubits is represented by a mixed state density matrix that is decoherent from a pure state. And from the purification picture, we can think about that we still have a pure state defined in large Hilbert space that contains system qubits together with ancillaries. And the quantum channel is equivalent to we add some local unitary operator to entangle them into an SPT-like state that has a measurement-induced long-range order. If I measure the ancillary degree of freedom post-measurement, the system qubits would have long-range order. And indeed, the Renyi-2 correlation function that could be a way to manifest strong to weak symmetry breaking is exactly equivalent to the fact that if we take 2 copies of any purified wave functions, make an EPR projections, and eventually we get a long-range order. So the simple take-home message we learn from this simple example is inner product is equivalent to EPR projection. So whenever you are doing a partial trace for the density matrix in the future to get a reduced density matrix, think about this process as doing some type of EPR projection for the wave function in the cat copy and the bra copy. Okay, so after this simple toy examples, let's look into the more general case. Let's consider a more general quantum channel. So now let me go to 2D because it's more stable. Suppose I have a 2D square lattice and I have all of the spin polarized in the x directions. And now I think about a general quantum channel that has a measurement rate at 2p. So I have some probability to measure all of the spin bilinear between the links. And for the other probability, I just leave it untouched and just a unitary operator that is identity. And for p equal 1/2, this reduced to a pure measurement quantum channel where I measure and average over all of the result. And if p is 0, then I'm not doing any measurement and do not do anything toward the pure wave function at all. So here, I will eventually get a mixed state density matrix that has a controllable parameter p. So again, let's make a purification view. Whenever we have a mixed state density matrix, I can think about it as a reduced density matrix of a purified wave function. So here in the purified space, the system degree of freedom of these blue spins live on the vertex, and the ancillary degree of freedom live on the links. And if I want to mimic something I introduced, that measurement or weak measurement quantum channel, what I need to do is still apply a 3-body gate to entangle them. And here, how I entangle them is if they are parallel to each other, I rotate it by a small angle theta. If they are anti-parallel to each other, I rotate it by 90 degree minus theta. And the theta, actually controls the measurement rate p. Okay, and let's look at a simple case when theta is 0. The wave function is pretty simple because the wave function turned out to be a short-range entangled wave function that is the ground state of a stabilizer Hamiltonian. And this stabilizer Hamiltonian was explored a while ago, but first pointed out by and that this turned out to be a SPT wave function that is protected by a one-form cross zero-form symmetry, where the zero-form symmetry acts on all of the system spins, and one-form symmetry only acts on the ancillary spins. It does not have any long-range order. However, it has a non-vanishing string order. If I measure the ZZ correlation function of the blue spin from the system, they're somehow modified by a charge string carried by the red spin from the ancillary. And hence, if we project all of the red spins to a specific sectors, what you will find is the post-projected wave function would have long-range order. And when we measure the Renyi-2 correlation function after we trace out all of the red spins and get the reduced density matrix, we're indeed doing a thought experiment that we duplicate the SPT wave function first, second copy, project all of the ancillary into an EPR pair, and measuring such kind of post-projected wave function, which is non-vanishing. But this is a special case where theta is 0 and p is 1/2. What about a more general case? So for p that is smaller than 1/2, it turns out a way that the decoration between the domain wall here is not perfect. They're not orthogonal to each other. And after we apply such kind of unitary, it's not hard to see that the Z2 symmetry of the system is always there because we need that strong symmetries. But the one-form symmetry that act on the ancillary degree of freedom would be broken weakly, provided that theta is finite or p is smaller than 1/2. So usually if we break this one-form symmetry explicitly in wave function, there is no notion of SPT because there is no symmetry, but one-form symmetry has a very intriguing feature. Even you weakly break it, you can have some type of emergent one-form symmetries, just like the toric code. And here, what we can demonstrate is that even we weakly break the one-form symmetries, the measurement induced the long-range order is still non-vanishing. And if we measure the strange correlator of this wave function for finite theta, where one-form symmetry is broken explicitly, it turns out that the strange correlator is still non-vanishing up to some threshold of theta, which means up to some threshold of p. We still have a strong to weak symmetry breaking that can appear at a finite measurement rate. Okay, good. So let me summarize. So what do we learn from this simple example of how symmetry, spontaneous strong to weak symmetry breaking can appear in a mixed state? And the most striking result for me, at least when I look into this specific example, is that it can be done by finite depth quantum channel, which is equivalent to finite depth local unitary acting on the purified waveform. And what happened here is, in the purified wave function, we somehow entangle the purified wave function into an SPT-like state. They don't have any long-range correlation function. But if we make a measurement to the ancillary degree of freedom, the post-measurement wave function would have a long-range order. And such kind of measurement-induced long-range order can be exactly manifest as the Renyi-2 correlation function. So whenever we have a strong to weak symmetry breaking, it actually indicates that our purified wave function have some type of conditional mutual information between the system and ancillary degree of freedom. And today I only talk about a specific Z2 symmetry case, but in principle we can seek about other symmetries, like we can seek about the spontaneous strong to weak symmetry for a continuous symmetry group, where in two spatial dimensions they can trigger something like a quasi-long-range order in 2D that is reminiscent of the classical BKT transition in 2D. We can think about a subsystem symmetry breaking. Usually it will happen at a finite rate in 3 spatial dimensions, or the spontaneous symmetry breaking of one-form symmetry where we get a mixed state, which is reminiscent of the mixed state topological order of the noisy toric code that was proposed and explored by someone in the audience here. Okay, so let me summarize. So today, what I show is that we can always understand the phase transition or spontaneous symmetry breaking in a mixed state in terms of the purification language. And in the mixed state, we are applying a quantum channel, and in a purification picture, we are applying unitary operator to entangle the system and the environment. And if the mixed state has a strong symmetry, that means the purified state has a symmetry that is only carried by the system alone. If the mixed state has a weak symmetry, that means your purified state have a symmetry that is carried by the system and then the ancillary together. And today we talk about the spontaneous strong to weak symmetry breaking mixed state. And I only introduced the Renyi-2 correlation function that is related with the EPR projection induced long-range order in the purified state. But like the talk 2 weeks ago, one company proposed that fidelity correlator is the true measurement of the phase transition. And this fidelity correlator could also have a measure in the purified wave function correspond to some optimal purification wave functions, strange correlators. And we can also extend the landscape of mixed state from the purification picture to study other exotic mixed states. Like there have been a bunch of exploration about mixed state SPTs, and it turns out that like Xu proposed for the mixed state SPT, a simple measure could be the type 2 strange correlators. And in the purified language, mixed state SPT also correspond to an SPT in the purified state. And the strange correlator, type 2 strange correlator, correspond to the annealed average of the strange correlator in the purified state. And there have been some proposals about the intrinsic mixed state SPT that does not have any analogy in pure wave functions. And it turns out that some of these intrinsic mixed state SPT can be linked to the subsystem SPT in a higher dimension as the reduced density matrix. And finally, there have been some explorations during the discussion section of this program about how do we detect mixed state anomaly. And if we have a mixed state anomaly between the strong and weak symmetry, say at the boundary of some mixed state SPT, it corresponds to the fact that in the purified state, there is also a mixed anomaly in the pure state that is between a subsystem symmetries and a global symmetries. So I hope I'm not running out of time. And finally, let me just end my talk. And the only take-home message I hope everyone can remember is whenever we are doing inner product, you are doing EPR projection. Thank you.
So for the continuous symmetry, what's the purified state that?
Okay, so the continuous symmetry is actually, I only find a purified state for the p equal 1/2 limit. And what is the purified state is it's something like the boson quantum Hall where you only have an off-diagonal K matrix, or something like quantum spin Hall effect where there's a mixed anomaly between the spin U1 symmetry and charge U1 symmetry. And I assume that the spin degree of freedom belong to the ancillary and the charge degree of freedom belong to the system. We know for quantum spin Hall effect or that boson quantum Hall, we have a non-vanishing string order parameter that the charge correlation is modulated by a string operator that connect them, and it has a power law decay correlation function. So if I trace out all of the ancillary, which correspond to the spin degree of freedom, the charge operator would have a power law decay correlation function. But one issue is here the exponent of the power law decay correlation function is usually not universal and depend on the microscopic detail of the wave function, purified wave function.
Yeah, when you're using this quantum channel to reduce this symmetry breaking transition, there's something happen in the purified states. Mm-hmm. But you also mentioned that to see something, you need to do the measurement in a purified state. Mm-hmm. But if you do not do measurement in a purified state, just purified state, whether there's some phase transition mm-hmm. in the purified state mm-hmm. Before you do measurement. Mm-hmm.
So here's the thing. I'm doing an imaginary experiment measurement. If I just have one copy and I have to do a measurement and have post-selection or know the result to do some error correction in order to figure out the long-range order. But for the environment degree of freedom, I assume I'm not accessible at all, so everything is lost. And that is why I need to make that trip, and that is why we need to go to Renyi-2. Renyi-2 corresponds to the fact that I have 2 copies of the purified state, and I have to do some EPR projection. And this EPR projection of the ancillary from the first and second copy is an imaginary experiment because this EPR projection corresponds to the Renyi-2 correlation function is equivalent to EPR projections for the first and second copy to be the same, is equivalent to trace out all of the ancillary in doing the inner product. So I'm not doing a physical projection, but in order to do something like a physical projection of the 2 copies, I have to go to the Renyi-2 correlation function.
The question is that just not for the physical measurement, just using this formality, just in the purified states, where the purified state can directly reflect the symmetry breaking in the original problem. For example, you have a quantum channel-induced symmetry breaking, and then in purified state you have this unitary measurement. Then do you have a unitary measurement that induced something in purified state with the correspond to this quantum channel-induced symmetry breaking?
I see. So there are one-to-one correspondence that I add some type of unitary gate to the purified wave function, and then I can tell if I trace out the ancillary degree of freedom, the reduced density matrix, whether it has symmetry break or not.
But if you do not trace out the ancillary degree of freedom, just look at the pure states. Whether the pure state have some feature which corresponds to the symmetry breaking you mentioned induced by quantum channel.
I see. So one thing.
In this case, the feature in purified state will be induced by the unitary transformation.
Okay. So first, the essential feature, sufficient feature, but may not be essential feature, is that your purified wave function, after apply the unitary, have to have some type of measurement induced long-range order, or it can be defined explicitly in terms of the conditional mutual information proposed and proved by Andrew Porter and Surround. But this is just a lower bound, which tells you that if you have this, then I must have that long-range order if I trace it out. And the second question is probably, so what type of unitary gate do I need to apply in order to get such kind of state that can trigger the reduced density matrix? And is there a way to classify the unitary gate? Honestly, I don't have a simple answer for that, but I remember Ruben Verensen had a zoology exploration of the pivot Hamiltonian that can apply unitary gate to get such kind of SPT wave functions, which indeed have conditional mutual information. But honestly, I don't have a concrete answer.
Yeah, I was wondering if there's anything special about second Rayleigh entropy. You can use higher Rayleigh, or as long as it's nonlinear, it's enough. Or
correct. So this is just one way to do that. In principle, you can consider Ren-En, and actually the Q measurement should be something like a fidelity operators. But the bottom line is it must be nonlinear in the density matrix, because your purified state does not have long-range order. Your mixed state, reduced density matrix won't have any long-range order.
Okay.
Related question. How easy is it to calculate the Renyi-2 correlation function in an actual experiment?
So how easy is it to calculate the Renyi-2 correlation function, or is there a way to prop the Renyi-2? Honestly, I don't know. I think actually Lee had some type of proposals in his paper with Xu, but I don't think this is really related to some experiment that can be done the other day, say on Google AI or something like that.
Thank you.
So is there a hierarchy of transitions between conventional long-range order, Renyi-2 long-range order, 3, 4, whatever? Are they all kind of, different, phases when certain correlators vanish, or are they only 2 phases? Where conventional long-range order and this other long-range order?
Yes. So if you calculate different quantities that are all nonlinear in the density matrix, the critical point which characterize, if you use them as measure, would be different. And the true measurement, which was demonstrated by Chen Wang and John's talk 2 weeks ago, with the fidelity operators. And if you say 2D Ising case, if you calculate that fidelity operator, you will see that the phase transition is reminiscent of the 2D classical random bound Ising model along the Nishimori line. And for Renyi-2, it is just similar to the 2D classical Ising model at finite temperature. And for Renyi-3, it is related to some type of Potts model. And for Renyi-N, it corresponds to a different critical PC.
And they all are at different parameters.
Yeah, they're different.
Thank you.
Slide near the end about mixed state topological order. Can you briefly explain?
Yeah, so it's just with a question mark, so it's not a rigorous. So it has been explored that we have mixed state topological order, and in particular, there could be some intrinsic mixed state topological order that has non-modular anyons theories proposed by Chen and Prem's group. And it turns out that a conjecture is in the purified language. Purification is not unique. This is just one purification. We can think about a purification wave function as a 3D topological wave function on an open boundary. And the mixed state density matrix is the reduced density matrix for the top layer by tracing out all of the bottom layers. And the weak one-form symmetries can be characterized by the two-form symmetry in the 3D bulk, and they can touch on the open boundary at the surface, and that act like a weak one-form symmetry. But this is just one way of purification, and recently I think Chen actually shows from the subsystem code that there can be a more concrete purification of the mixed state topological order, especially intrinsic mixed state topological order.
So you define your mixed state topological order by having a weak one-form symmetry, or how do you define your weak mixed state topological order? Like, what's the symmetry properties of your mixed state topological order? Do you require a weak one-form symmetry or two weak one-form symmetries with mixed anomaly, or something else?
Yes. So for the simple case, we actually have one weak one-form symmetry, and the other is a strong one-form symmetry, and then they can have two anomaly. And I'm not pretty sure about one-form symmetry, but at least for weak symmetries, if you only have weak symmetry in a mixed state density matrix, there cannot be any anomaly.
Other quick questions? Okay, great. Let's thank Yizhi again.